No. He's going to pick up one of his speakers.
Oh, wow.
Yeah. So
Yeah, this is the decision.
I showed him all the stuff.
Everything. Okay, great.
In 20 minutes.
That's good. Oh wow, you can do it in 20 minutes.
Well, this is supposed to be before 40 to 45 minutes.
Good. So you some.
I skipped some.
Down.
Yeah. Just give him the main idea.
All right, great.
Yeah, I can do it in 15 to 20 minutes.
No, please. Take your time.
It's the way. That's like
Right. Well, I guess we can start. Perfect. Well, thank you everyone for coming. This is our second condensed matter condensed matter biophysics sort of seminar this year. And we are really glad to have Cong S here from Yale. So he made a very long trip this morning.
It's okay.
It was smooth. Yeah, no, fantastic. Thanks for coming. Cong S did his PhD at MIT with Jing Kong and Jing Li, and then went on to do a postdoc, right, at Berkeley, right afterwards with Alex Settle.
Yes.
He is like one of the last postdocs, second to last, technically the last, still higher than Alex Settle, so a postdoc, and then accepted an assistant professor position in applied physics at Yale, and so
mechanical engineering, material science, and also applied.
and applied physics.
Yeah, the
so
main requirement is this.
I'm building the link to physics here, yeah, and so Jing Kong and Zettel, it's like synthesis and electron microscopy, at least in my head. So yeah, very, very big names in the field. And you're carrying this forward in very interesting directions and setting up the lab right now. So we're really looking forward to your take on atomic control at the, using electron beams, quantum materials. So the floor is yours.
All right, thank you so much, Cliff. Thank you. First of all, how many of you are from physics? Oh, almost all of you. Okay, how many of you are from engineering? Okay, all right. So yeah, so this talk is tailored for physics. It's not like, but you will see a lot of technical development here. We're trying to develop an atomic control method using electron microscope, and we developed a lot of method for synthesizing 2D materials and how we can make freestanding monolayer materials. But I'm going to show you some of the physics stuff later on. So yeah, thanks for the kind introduction. I'm actually affiliated to several different departments, but from Yale University in general. So just to give you a little bit of an overview of what my research group is doing, it's called Atom E Research Group. So one part of my research group does synthesis and devices. So we use chemical vapor deposition to grow monolayer 2D systems on top of a wafer or on top of a foil. And we use solution growth or flux method to grow some bulk materials like hexagonal boron nitride. We also investigate some physics and devices like metal semiconductor contact. So that forms the foundation of where our material is coming from. Because what we found, well, when I was a PhD student, I found that, yeah, usually you need to box some other groups for materials as a characterization person. So it's good to have some capability of preparing materials on our own. But on the other hand, the other half of the group is doing electron microscopy and spectroscopy. One topic we're going to cover today is the atom control, and the other is the atomic spectroscopy using electron microscope. We recently are pretty interested in this multi-probe electron microscopy, where we could co-localize the laser and an electron beam at the same place. So we could image the atomic structure of the material when it's in the photoexcited state. Okay, this is just for fun. So we have a group logo, which is something we're pretty proud of. So this is A, and that E So this is the electron trajectory around an atom, which shows this half of the group, and this is the layered material, which shows that half of the group. So yeah, just for fun. All right, so that's the content for today. We're going to talk a little bit about atom control. I'm trying to squeeze some of the fun things into this talk. The second part is on the quantum emitters. That's after we have this capability of controlling atoms, after we have the method of creating atomic defects, how we can apply those defects. The third part is on the excitonic band structure of monolayer HBM, which is a controversial topic that everybody is still debating on. Okay, so the first part is atom control. Why do we want to do atom control? There exists some atom control techniques that's pretty well known. So some of you might have seen this IBM character, right? So that's made by this scanning tunneling microscope where you have a metal probe, you're trying to drag it and nudge it on top of another surface to form a layout of an atom. So that's scanning tunneling microscope. And then there are other methods like optical tweezer where you use like lasers to confine the atom into a very small space, and you can use it to cool an atom. So that forms the basics of ultra cold atoms. And they all lead to, well, Nobel Prizes in physics. So that's for yeah. Hopefully some of you will get this prize by having some of the nice ideas and contributed to some techniques. But, well, even though they got a Nobel Prize, I have to say there are lots of confinements and there are a lot of limitations on these. So for STM, the atomic structure has to be stabilized by a very, very low temperature. Once you heat it up to room temperature, these atomic structures evaporate. So they no longer stay on the surface. For optical tweezer, of course, you need to have optical laser source, you need to have vacuum chamber. So these are the limitations that cannot make these techniques to go further upscale. So that they're good for lab, but it's probably not good for daily application. And so I want to introduce you to a concept that I came up with. It's called atomic engineering. So when you add some engineering flavor into atom control, what you want is to add some applicability and some practicality into atom control so that the atomic structure that you create could exist, for example, in room temperature, in ambient condition. So there are two definitions. The first definition is on the practices of changing the atomic structure of solid-state matter to the precision of single atom, and we want it to be at room temperature. So room temperature atom control would be useful in a lot of cases. And the second is on the application side, so exploiting atomic structure, ideally stable in air and room temperature for all kinds of applications. So that's what I mean by saying atomic engineering. And the motivation behind this, why do we want atomic engineering, even though it's quite obvious probably to some of you, but I still want to point out, quantum information science, they're defect structures that is being used as the basic qubit. Transistors, they're this Moore's law that brings the size of these transistors down to, at some time, will hit the single atom level. So we need to have some method for controlling atoms eventually. Of course, when you have some atomic structure that you could design, it leads to some very interesting physical phenomena. And in chemistry, people are also interested in these atomic structure because of single atom catalysis. So these are all the motivations, oops, sorry about that, behind, well, the development of this, what I call atomic engineering. Why do we need it? So I'm hoping to use this single slide to convince you that electron beam might be our only hope to realize atomic engineering. Not when you compare with any other techniques, electron beam might be the only hope. So in this diagram, the x-axis represents the spatial resolution of the probe. The farther to the left, the better resolution it is. And the y-axis represents the energy range. So what is the energy range that a specific technique is actually covering? There are these many, well, a typical probe that you could get. You could get a neutron probe, there are neutron particles hitting the sample. You could have a photon source. You could have an ion source. You could have an electron source. And of course, you could have the scanning probe microscopy where you have this metal. So they're roughly laid in this relative positions. So neutron has a worse spatial resolution. Photon has a little bit better spatial resolution. Ion has even better. Electron and SPM has the highest spatial resolution. But what's also interesting is that their energy range covers different areas. So if I draw a vertical line representing the atom spacing, which is roughly 1 angstrom, that goes here. And now I draw a horizontal line. This horizontal line represents the bond breaking energy, that is, the energy needed for bond breaking in crystal, which is roughly on the order of 5 to 10 eV. So one chemical bond is roughly on the order of 1 eV, and if you have several of them connecting to an atom, those atoms are tightly bonded in the crystal with a 5 to 10 eV of energy. So if you want to really break the bond of these atoms, you at least need an energy range that's above 5 to 10 eV. And the reason why this is so important is because we learned that from SPM. If an atom doesn't have the bond to stabilize the structure, they will simply evaporate in room temperature. So you no longer get a stable atomic structure there. You would need to have a technique that has that capability of breaking bonds and form a crystal so that this atomic engineering, the whole idea of atomic engineering could work. And then I just highlight this area. This area is what I call atomic engineering viable zone. So you need to have a technique that has a higher energy than this bond breaking line. And you need to have a higher spatial resolution than the atomic spacing. And you can see that electron might be the only technique that we're able to do atomic engineering at this time. So that's why all my following talk will be based on TEM, or electron microscopy. So that's why we do electron microscopy for manipulating methods. Okay, so this is a typical, just for some of you who is not familiar with electron microscope. This is a typical scanning transmission electron microscope. This is a neon stem, has not a big market size. A better market is occupied by Thermo Fisher and JOL, but they almost have the same kind of layout. So if you look at the cross-section of this tool, you have an electron gun, which produces electrons, and they're going through a couple of electromagnetic lenses, and to be focused to be as sharp as a single atom. And then you scan this electron beam across a sample to form signals, and those signals, the scattered electron beam could be captured by what is called the ADF detector to form atomic images. And some of the beam going through this could be spread out by a prism so that you could get spectroscopy, local spectroscopy of a single atom. The electron is usually operated at 30 to 200 keV, and this is the spectroscopy is called EELS, electron energy loss spectroscopy, which we'll briefly cover in our later slides. Okay, so that's an STEM. When you put your sample into an STEM, because the electron is having a very high acceleration voltage, it goes through the sample and transferring a certain amount of energy to the material. So it could potentially make some changes to the material. When it's uncontrollable, you could cause a lot of damage to the material. That's called electron beam irradiation damage. But in this case, I used a phosphorus doped graphene. And I look at this single phosphorus dopant, and you could see that under the beam scanning, this little dopant is actually doing a lot of kinds of dynamics. In this case, it's what we call direct exchange, where the phosphorus atom exchanges sites with the neighbor carbon atom, and Stone-Wills transition is basically rotating by 90 degrees at a time. So the whole idea of atom control is to make all these random process. If you could make this random process into a deterministic process, we could call it a control. So our whole idea is to make these to be deterministic. If it's random, it's called irradiation damage. If it's deterministic, it's atom control. So that's how we define it, which makes sense, actually. Okay, So imagine yourself as an electron flying toward an atom. This is a typical length scale that you're going to expect to see. When you're flying a little bit close to that atom, the first thing you're going to see are the valence electrons, which is roughly on the order of angstrom. And when you're getting closer, then you could have those core electrons, which are tightly bound to the nucleus. They're roughly on the order of a quarter. For example, for carbon atom, it's a quarter in size of the valence electrons. And when you could fly a little bit closer to the nucleus with a more precise range in target, you could fly very close to the nucleus. If it hits in this target, it could transfer about 1 eV to the target atom. The way how you could transfer that energy is through Coulomb interaction. Electron has negative charge, your nucleus has positive charge. When it moves around, it transfers a certain amount of energy and momentum. So when you fly into this picometer range, 1 eV energy could be transferred. If you really want to get those atoms to jump, what you saw in those videos, 10 femtometer is almost the target range. This is when you can have the target atom or the primary knock-on. Well, there's a terminology called primary knock-on atom to make a lot of dynamics. So this is the little target that the electron has to fly in. That's a cross-section of atom dynamics. Okay, so in terms of time scale, well, the first thing that a high energy electron could do is to transfer energy and momentum to a nucleus, and that's what we call elastic collision. And the elastic collision happens in what is called 1 zeptosecond. I don't know how many of you know this scale is 10 to the minus 21. So it's a very fast process. There are also what we call inelastic collision, where the high energy electron could transfer some energy to the electrons in the crystal so that it could excite the material. And that inelastic collision happens on the order of attosecond. Once you have that material goes to the excited state, it takes about femtosecond for a metallic material to get back to its ground state. So that's a time scale. Once you have this elastic collision, your lattice is going to vibrate. So it takes about picosecond on the time scale to have the lattice vibration to relax back to a near ground state. So that's also the phonon lifetime. It's on the range of this order. So for the brightest electron source you could possibly get, which is a cold field emission source, the electron interval time, so that's marking the time interval between the two electrons hitting the atom one at a time, is on the order of nanosecond. So even with the brightest electron source, you still get nanosecond time interval. So what you can see is these time scales are very well separated with each other. So when you see that, you know, okay, if I want to simulate any of those, I could basically consider one, well, considering the other to be not happening or has already happened and fully relaxed. So that's a good thing for us. All right, so let's take a look. So if we only care about the elastic collision, because we care about atom dynamics, so let's forget about the inelastic collision at this time. Assuming it's all on the ground state and everything happens when the material is not excited. So the elastic collision, if you see this, well, let's assume that this is an electron. That's a nucleus. So in a head-up collision scenario, it could transfer the maximum amount of energy to that nucleus. And if it's just a little bit off the path, this is actually called impact parameter. If that impact parameter is larger than 0, then this is going to happen. So transfer a little bit less, and the momentum is going to go a little bit sideways. If it goes further, that's what the target atom would look like in terms of its energy and momentum. So if you plot the possible energy momentum distribution of this target atom, for example, in this case it's a carbon, hit by an electron, the possible distribution of energy if it's being characterized by this spherical coordinate, would look like an ovoid. So the possible distribution of that atom is on the shell of this ovoid. And this is what we called energy momentum distribution of an atom, and you can simply call it an ovoid. This marks the possible carbon status. And then once the carbon gets hit by an electron, then the lattice starts to vibrate and there will be dynamics starts to evolve. How can we simulate that? There's actually one way to simulate that. That is by using ab initio molecular dynamics. So in this case, we could recover the direct exchange scenario where you have those two atoms exchange their sites. Once you give this carbon atom an initial kick and let it just evolve, you could see that the carbon just go around, and then this phosphorus atom actually bounce down, and then they switch their sites. So we could use these ab initio molecular dynamics to reproduce what we're seeing inside an electron microscope. And the same thing goes to Stone-Wills transition. If the carbon atom actually is kicked a little bit sideways, you could also lead to this Stone-Wills transition. So in this case, it's a pure ab initio calculation, shows what we observed here. All right. So now what you can do is you sample the space. If you assume that the carbon atom could have a different variety, a different combination of energy plus momentum, and then you dump them into the ab initio calculation and let the lattice evolve, what you can do is you can sample the whole space and calculate what the outcome of different initial momentum look like. And then you could partition the whole space into different color blocks representing different outcomes. So in this case, we're using the blue block to represent direct exchange, what you saw in the first slide, and then use the magenta or pink block to represent the Stone-Wills transition. So they look like that. This is what we call outcome function. If you combine the ovoid, we still remember there's an ovoid representing the initial status of that atom. If you combine these two together, there will be an intersection area which marks the active dynamic region. Basically, it tells you that once your carbon atom is being kicked by an electron and is scattered to this, what would the dynamic outcome look like? So if there is an intersection between these two things, it means there's a probability that this dynamics could be an outcome. So by calculating the ratio of these different intersections actually marks the probability of different atoms, how it would look like when it's being kicked by an atom. So, okay, so this is what we call primary knock-on space, because the carbon atom is actually called the primary knock-on atom in particle physics. So, okay, so just a little bit, just to give you two examples, how this PKS, primary knock-on space, could be used. One is, remember, we want to make a random process into a deterministic process. So biasing the probability of these dynamics is one of the very central target that we need to achieve. So how can we bias dynamics? It turns out that the direction of that ovoid you were seeing, it actually changes with respect to the incident direction of the electron beam. So when the electron beam is hitting this way of the carbon atom, then that ovoid will tilt. So that tilts with the electron beam tilting angle. And in this case, what you can see is when this ovoid tilts sideways, there are some cases that only one color block will be activated, and all the other color block will be suppressed. So in that case, you could bias the dynamic outcome into one certain type of atom dynamics instead of having all the other atom dynamics happening all the time. So we did this thing, we did an experiment. We put the electron probe, tilted a little bit in this way, and according to PKS, it only intersects with the clockwise Stone-Wills transition. And this is what we see actually in the experiment. We see that it only has this Stone-Wills transition that happens once you place the electron beam in that way. without having the direct exchange or other kinds of, or even a counterclockwise zone transition. So this is a proof of concept, how you could use PKS in a simple way to visualize the outcome.
So sorry.
Yes.
Can you just quickly explain, like, you have the beam and you also need the beam to image, right? So what is
Yes.
the difference? Like, do you just like hit it for a certain dose or time and then you switch and you take your STM image at a lower dose or something? Or
No, in this case, we tilt the sample instead. So instead of tilting the beam, we tilt the sample in this way so that it doesn't really affect the electron beam path. So it still goes scattered with the material, still forms all the images as if it's in a normal imaging condition, but your sample is actually tilted in this combination of angles. Yeah. Okay, the other very quick application is what we call Doppler amplification effect. Is when the lattice is actually vibrating, the ovoid is not in a fixed shape because when the lattice is vibrating away from the electron beam, then it will actually there will be more energy transferred from the electron to the material. If it's moving toward the electron beam, there will be less energy that could be transferred from electron to. An intuitive way of understanding this is assuming there is a truck that comes to you. Everybody knows Doppler effect. If there is a truck that comes to you when you yell at it, there's a higher pitch that is being reflected when it's coming to you, and when the truck is going away, the pitch gets lower. Which means when the truck is moving towards you, the reflected sound actually has a higher energy, so that there is less energy that could be transferred to that truck. And when it's moving away from you, there is a lower energy that's reflected back, so there's more energy that's transferred to the truck. In this case, the lattice is the truck, and the electron beam is the sound wave. So when it's moving away from you, more energy. Okay, so that actually, the shrinking and expanding ovoid actually depicts the real scenario when there is actually a lattice vibration. And it actually intersect with the color blocks from time to time. And when you have a more dramatic temperature change, then it will intersect with more color blocks. So the displacement cross-section or the atom dynamic cross-section will become bigger. So this is what we are seeing from our experiment. At a lower temperature, these are all the frames showing one single dopant that's sustained across 251 frames. But once we change the temperature to 1,000 Celsius and we emit the same dopant, it just got knocked out away almost instantaneously. So there is definitely a temperature-dependent atom displacement here. So those are some of the very intuitive way of applying the PKS. So I'm not the only one who's doing this. There are other groups in the world. Thomas Susi from University of Vienna, Andre Dick from Oak Ridge National Lab, Shi Ze, actually we recently hired him as a new director for this electron microscopy facility, who all tried this. And this is actually a beautiful demonstration from Toma. By using the same idea, you could just guide the silicon atom to jump around a hexagonal ring of a graphene and let it jump across that 6 different sites. And this also applies to aluminum and graphene, and in some cases, it also applies to a dopant in MOS2. So that's how we got atom jump. And well, we could envision a little bit about the future of atom control. We have this STEM. Once it takes all the crystal structures, there's supposed to be some structural recognition that could automatically identify what this local structure looked like. And then all these PKS database could be pre-calculated and stored in a database, and you retrieve them and feed them into the PKS theory, and the PKS theory could give you an input of an STM telling it, okay, this is what you need to do in order to better control an atom. So this makes the workflow of an automatic atom control. And you can see that the structural recognition is actually quite an important link. So one of my students here at Yale, staff, is working on using machine learning to do atom recognition. So this is one example showing a monolayer MOS2 from experiment without any processing. We could use this model to predict where the different atom is, where the sulfur atoms are, where the molybdenum atoms are, whether there are defects or not. So yeah, so that's an ongoing project, but we hope we could fill this gap and make a complete feedback loop for controlling atom using STM. And then let's come to the second part. Why do we care about atom control? How can we make use of these atomic structure? So one thing that actually is pretty actively investigated is called quantum emitters, single photon emitters. Okay, I'm going to go through this quickly. There are different candidates for hosting quantum information sciences to be the qubit. There's superconducting circuits, quantum dots, color centers, trapped ions, and these topological protected systems, which we still haven't proved yet experimentally. Excuse me. So you could categorize them into two groups. Color center stands out from the rest because it's the only possible platform that could host small-scale devices and communication network. Sorry. Do you mind if I go to?
It's okay, of course.
Apologize for that.
If you exit that side and go straight that side. Okay. You just go straight.
Really apologize for that. Sometimes when I speak too fast, it happens. Whew. Yeah, just take this time to take a breath. Yeah. There are too many things I want to cover. Whew. All the rest of the techniques, they have to sustain by low temperature, ultra high vacuum, or laser. So you can't, they can't be portable. There are many different applications for color centers: magnetometry, sensing, simulation, quantum computing, quantum networks. The material I'm using is called HBN. So it's hexagonal boron nitride with a hexagonal lattice and an optical band gap of almost 6 eV. And we use cathodoluminescence to probe the emission spectroscopy. It's an equivalent technique of photoluminescence, but instead of using laser as the excitation source, we use electron beam. So that's the cathodoluminescence. In HBN, people have discovered a wide range of color centers, from DPV all the way to the IR. But they all look like that. So they're all distributed randomly. People use ion implantation to create these defects and make them bright, but it's very hard to control their location or control their on-off state. So everything's random. What we found was just straightly get to the final conclusion. We found that by having a twist, by twisting 2-volt HBM. At the twisted interface, you can see there are some UV emitters getting activated. If you compare that with a 0-degree stacking, which doesn't have any twist, these actually, B and E, they form it's actually a panchromatic photon count map, which shows that at the twisted interface, it doesn't really have any increase in emission. But whenever you have a twist, there's something that emits. It becomes really bright. And if we zoom in, we still see that those are individual defects. We take the spectrum, and it turns out that this is a very well-known defect. It's called 4EV defect in HBM. So people just give it a name because the zero phonon line is located right at 4EV. Somebody took the G2 measurement, which characterized its single photon state, whether it emits one photon at a time, and they have proved that this is a single photon emitter. Okay, and we did some correlation between photon counts, how bright it becomes with a twist angle. So from 0, you could see there's almost no photon that's actually being enhanced. But once you give it a twist all the way up to 30, there's a pretty high, give it a huge boost in terms of its defect emission. There's almost like 50 to 100-fold of brightness change here. So that was a way how you could turn some emitters from off state to an on state by just giving it a twist. There's also, it turns out that we also figured out a way to make those twisted bright emitters to become dark again. This is just by adding 2 electrodes encapsulating the twisted HBM feature at a vertical voltage. And then this is the peak that originally was emitted by that 4EV emitter. But once you add a vertical voltage, most of the emission got quenched. So it becomes pretty dark. And if you look at what is called the electron beam induced current, which is the current going through this circuit whenever there is an E-beam excitation, it has an anti-correlation relation with the UV photon counts. So whenever you have a higher E-beam, you get a lower UV photon count. So which means that the excitons, which are used to recombine and produce those UV photons, they become EBIC. They become a current. So these are coming. So we proved that these 2 things are actually having the same origin, which is the band edge exciton. Okay, and the third thing we demonstrated is that by using E-beam, this is our ultimate dream, is to use E-beam to deterministically seed defect into some patterns, and we choose a species of these defects. So we did some very simple demonstration and found that with a longer dwell time of this E-beam on a single spot, we could make it brighter and brighter, and we can even draw a smiley face pattern there. And by comparing the emission spectroscopy, we could see that the radiation-induced defects, or these emitters, are actually the same with the twisted HBM. So they're coming from the same source. But the question is, what are the origins of these defect emission? What are they? It's still debated. People are still debating what they are, what this very famous 4EV emitter is. One work that actually did a pretty good job in predicting the spectrum is from this paper, which shows almost a complete, this is mirror symmetry. So they go from 409 back to 350. This is going from the left to the right. And you could see they almost reproduce the shape of what we're seeing in our CL experiment. So we tend to believe, okay, maybe it's a double carbon, it's called the carbon dimer, where one carbon is substituting a boron atom, and the other carbon is substituting a nitrogen atom. So that's maybe the origin. And there are also some other work saying it's a self-tracked exciton. Well, yeah, we don't know, unless we see it clearly inside some sort of imaging technique like an STM. If you're really interested in this topic, this is some what we call tutorial articles we recently published, which has more than 100 pages. So it's a pretty long review article. And it covers a lot of the previous optics applications of HBN. What I want to say is there's one topic that people are still unclear. It's a simple question. So whether monolayer HBN is a direct bandgap insulator or indirect bandgap insulator, we don't know that. Nobody knows. There's some predictions coming from the theory side says it's an indirect bandgap. There's some experimental work saying it's a direct bandgap. So that's why I highlighted this topic as one of the sections in there, which is the third section of our topic, which is something that we're working on recently. We got some very nice data like 2 weeks ago. So I'm just showing it to you. These are the fresh data. Okay, so I'm just trying to show you how we got those 2D material. Like CVD, we could grow using solid phase precursors, liquid phase precursors. We could grow all kinds of 2D material. We could get very big single crystal monolayer material. So these flakes, if you look at it using your with your naked eye, you could see a single flake, which is 1 monolayer thick. So they're pretty big. And you could also float them on water. So this is a piece of monolayer MOS2 floating on water, which you could use a tweezer to poke around, which is actually kind of fun. When you imagine it's a monolayer, it's a single atom layer, it's quite fun to play with. And we recently figured out a way to transfer monolayer HBN to the TM grid so that it makes a freestanding material. The outcome is that for monolayer HBN, we could get a pretty nice coverage. And then we could also repeat the process and create a bilayer HBN where we could get different twisted regions, which is very important for investigating that twisted HBN, what the mechanism is, right? So these are something we're pretty excited about, but okay, so now we get all kinds of freestanding monolayer. We could have graphene, which I showed you how we could manipulate atoms. We could have HBN, which is an insulator, and all kinds of TMDs. These are the atomic images for HBN, 1 layer or twisted bilayer where there's a moire pattern. We can also grow pristine TMD, like in this case MOS2, or a doped MOS2. Or we could make these hero structures, stack them, combine whatever way you want it to be. Okay, so this is something that we're working on. We want to answer the question whether monolayer HBN is a direct bandgap or has a direct bandgap or indirect bandgap. The technique we use is also inside an STM. It's called momentum resolved EELs, where when the beam goes across the sample, you spread out them. So there's a diffraction plane here, which marks the Q space. It's actually the momentum space. And then we further spread them out in the energy space. So you spread them twice. 1 degree of freedom is the momentum freedom, and then the energy freedom, which you could plot a band structure out from this. This is the momentum resolved EELs. I want to say this is actually in charge by my student Luna, and in collaboration with Steffi from Oak Ridge and Diana from Yale. So this is a GWBSE calculation of the monolayer HBN. Basically, it shows that for GW calculation, the electronic band structure still shows a perfect indirect bandgap configuration. So this, from this point to that point, actually forms the lowest energy difference. But when we add exciton effect, the binding energy of exciton effect, into this, we found that actually the Rydberg state at this Q equals to level status state, it actually has a larger binding energy. So the energy shift of a real exciton is actually more than this part. So which makes, this is an excitonic band structure, which makes the gamma point. So these are actually marks the momentum of an exciton. So gamma means Q equals to 0, K means Q equals to K, and they're almost identical. it's hard to distinguish which one has a higher energy, which one doesn't. And what's also interesting is that for this point, it's actually a dark excitonic band. So it's forbidden to jump from here to there, actually. So the lowest, so from theoretical calculation, we predict that HBN is an optically direct bandgap insulator. So only the gamma point is bright. There's a blue band, which we call exciton bright band number 1, and the pink band is called the exciton band number 2. What's also interesting is that the pink band has a linear dispersion relation. So at this gamma point, you see that they form like a direct cone, which means in this case, the exciton doesn't have any mass. It's a massless exciton which acts like as a photon. Okay, and from this theoretical calculation, we can also predict what it should look like inside a momentum resolved EOS experiment. This is theory, and this is what we got from experiment. And instantaneously could see that there's a pretty good match when it comes to this pink band. Starting from the gamma point, it's actually low in energy, but once you go away from the gamma point, that peak shifts dramatically. So it matches quite well with the theoretical prediction, which actually confirms that this linear dispersion of exciton actually exists. And this is not a new topic. So Diana did this almost 10 years ago, using GW calculation, predict the light-like exciton dispersion in TND sample. But I believe nobody has ever observed it experimentally. So we were quite excited to confirm that in HBN, it also has this linear dispersion, and we could confirm it experimentally that it does exist here. But the side note is HBN is an optically direct bandgap material with a dark mode that has a comparable energy with it. So that's our understanding of what a monolayer HBN should be like. And the reason why we're interested in this is because we're interested in the defect emission. So knowing the whole excitonic decay path would be very informative for us to learn what happens with those defects. All right, so we covered atom control, we covered CL and quantum emitter, we covered the freestanding monolayer HBM, and it's great if we could combine them together. And if we could demonstrate their atom, actually, we could see those atomic defects in atomic precision in the future. But that requires a pretty high-end machine for us to do that. So this is at Yale, where we're getting, hopefully by the end of this year, we're getting a pretty good STM with a very high resolution, spatial resolution, better than 50 picometer. But what's special about the Spectra Ultra is that it has a laser injection capability. There is an atom-like Monk CL. It's a parabolic mirror that goes above the sample. So we could do laser injection. We could do CL, photoluminescence, and we could also, in principle, do PL in there. And once we combine them, then we could possibly figure out a way, which is some of our ultimate goal is how to create these quantum emitters atom by atom and having them laid out in some patterns that we need. Okay, so with that, apart from thanking my group members, which I've already shown you, these are all my collaborators, all my mentors, advisors who helped me along the way, and of course the funding agency who made this possible. All right, thank you for your attention.
Thank you, Cong. Any questions for Cong?
How are you sure, or are you sure that you get a single electron interaction, the single out of control, using the electron microscope? You turn on the source and you turn off the source. Can you do that fast enough that you expect there's just one electron coming in, or do you expect that you get multiple interactions during that process?
Yeah, you definitely get multiple interactions because there's no way for you to confine the electron beam to be in that specific little target. The electron beam has a width of around 1 angstrom. So each time when an electron comes into your material, it could go sideways, it could not lead to any dynamics. So what you need to do is to park your beam there until there is an expected dynamics that comes, and then you just turn off the electron beam. For example, you want to knock out a specific atom, you just park it there until it knocks it out, you turn off the beam, and then you could do some other atom manipulation in the following steps. Yeah, you never control a single electron to fly. There's no way you could control that.
How do you know that that atom has gotten knocked?
Oh, okay. There are many ways to know that. For example, when an atom knocks, well, statistically, it's actually a math problem. There are scattering cross-section associated with different dynamic problems. So you could calculate the cross-section of that and expect how much time you need to park your beam there to expect one knock-on event to happen. What you can do is park your beam there for for enough time, and then do a very quick scan to see if that actually leads to that desired outcome. And then if it doesn't, park your beam again, repeat the same process.
Yeah, that's kind of what I was getting at. It seems like it would be, there's kind of stochasticity probably.
Yes,
that would
yes.
be built into it.
Yes. So the electron beam dose that's required for making those dynamics happen is way higher than imaging.
Mm-hmm.
So that actually makes it easier for you to confirm whether there's an atomic structural change or not.
Mm.
Yeah, of course.
Other questions? Yes.
In the GWBSE equation, I wonder what is the number of the number. Can you tell me how? Because I once do the GWBSE calculation, the simulation using VASP. So, but it seems that my result is not quite good. So, can you tell me what is the core parameter? I mean, the parameter should be choose wisely, and so I'm not sure.
Okay, so first of all, the GW calculation is not done by me. It's actually Diana is the expert, who is a student of Stephen Louis. The second thing is I would never recommend you to perform GW in VASP.
Oh.
So VASP is not optimized for GW. Their convergence is kind of horrible when you're applying BSE and GW scheme to the calculation. I think they're using quantum espresso and combined with Berkeley GW. That is a better way of performing. The convergence actually is getting much better. So yeah.
Other questions? Yes.
So you showed some temperature dependent data around like slide 20 or so.
Yes.
What were you doing in situ heating for the
You mean-
observation? I think it was slide 20.
1,000 degrees?
Yeah.
Oh,
The
that
1,000
one.
degree thing.
Yeah, this one.
Yeah.
Okay. What I'm trying to prove is that under high temperature, the
Yeah.
lattice starts to vibrate dramatically,
Right.
so that there's more probability that an atom could be knocked out,
Right.
or there could be more dynamics that could come out. So this is just to show you a proof of concept that at low temperature, it's quite stable. At high temperature, it starts to move around.
But you were actually heating the sample up
You're
when you were
heating the
imaging
sample
that.
up.
So what heating mechanism were you using?
That's true heating. You just
Okay,
have a MEMS
okay.
chip.
Yeah.
Mm-hmm.
Yeah.
Yeah.
Just a quick question. So in the top panel,
Yes.
what is the substrate for the graphene, or how can you know that it's flat?
Oh,
Like, how do
okay.
you control
So here, everything, in order to see atoms clearly, you have to make these monolayer freestanding.
Right.
So it has to suspend across a hole. So you look through the hole. There's only one layer of graphene that exists. There's no substrate underneath. So it's vacuum up, vacuum down.
And do you have any thought about like how strain could play a role, like in like strain defects in across those holes?
Yeah, if you have strain, you change the atomic configuration, it changes everything. It's definitely coupled with a lot of things. Yeah. So it changes everything. It's a little bit hard for us to apply strain. There are intrinsic strain associated with the monolayer. You could see there are ripples, of course. But that's a great question. Maybe there could be some ab initio molecular dynamics to be calculated, but adding a strain breaks symmetry, So I would assume that it makes certain type of dynamics to be easier and makes some other certain type of dynamic to be harder. So it breaks the symmetry of the whole space. Yeah.
Maybe on that note, I can
Yes.
ask a question. The 4eV emitter that you mentioned.
Yes.
So you suggest a structure for it. Like if you make these in your monolith, I have a few questions. Like what is like on that note? Do you expect like spectral variation depending on where you make it? Is a monolayer actually desirable? Wouldn't you prefer to embed those in a thicker layer of HBM? And if you want to do that, can you do that with your method, or what would be a way around to have it like in the center of like a thicker slab?
Yes.
So to like maybe more.
That's a great question. It definitely matters. So the environment matters a lot. If you have different stacking order of HBM, that changes its band structure intrinsically, so which could change the whole acetone decay path for sure. And you asked whether we're actually, one of the projects of my Eli, who's another postdoc, we're trying to use flux method to intentionally dope carbon into HBM. We want to see if it works. So in principle, what we could do is we could have some very thin carbon-doped HBN encapsulated by some very pristine HBN, see if that makes a lot of changes. So what is your other question?
I'm thinking of what you proposed for the atom engineering using E-beam.
Oh.
Is there a prospect for like making it in an embedded manner?
Yes. Well, you're actually touching on another problem that we actually care about is bulk versus monolayer. Which one is better? From a CL perspective, we've never seen any emission spectrum coming from a monolayer HBM. So which is a common phenomenon across the whole 2D material. Even for MOS2, when you make it freestanding, CL doesn't have anything unless you encapsulate it in HBM. So that's a bad thing. But the good thing about monolayer is that it gives us a clear atomic structure. So when we scan across it, we know what the atomic structure is. Whereas for bulk material, you don't really know what that defect is. We actually recently have a collaboration with Zhang Miao from UCLA. He did that tychography. It's multi-slice tychography, which allows you to go through the focus. So it goes through the sample in depth to try to show it like layers by layers with a depth resolution of 2.5 nanometer. But 2.5 nanometer still has almost 7 to 8 layers of HBM. So you still don't really know how what the structure looks like. So the advantage of having everything appear on a monolayer is that you could correlate what the atomic structure of those defect is. We actually, there's another project. We're trying to see whether we could bring the emission of a monolayer defect to be bright. Actually, we found some pretty tricky ways of doing it. We're still exploring it, but there is a pretty good progress to bring those monolayer defects and let it emit light. So yeah, there are trade-offs between bulk and the bulk material. It actually varies all the defect inside, which makes it more stable. So that's the advantage of a bulk.
Yeah.
You mentioned the single photon emitters in defected monolayer boron nitride.
Yes.
Right? Do you expect the twisted bilayer boron nitride to have the same single photon emittance? I don't know if there was any data on that either.
Well, what we showed for those twisted HBM are two bulk HBM twisted each other.
Oh, I see. Okay.
So those are not bilayer twisted.
Right. Okay.
Monolayer twist.
Yeah.
So those are not. But we would definitely like to see if a bilayer HBM could reproduce some of our observation in those bulk materials. There definitely will be a difference. So when you expose these defects as the surface, there are lots of charge problem, there's surface contamination. So a lot harder to deal with and compare with the bulk.
I also have another small question actually about the picture you have of the TMD floating on water. How did you How is
Oh.
that even possible? I guess.
Yeah. So
Like transferring it onto the water, I guess.
yeah, it's actually very simple.
Oh.
Once you grow it from using the CD method, there's certain type of condition of sample growth that allows you to have those sample that's on the wafer, and you just directly insert that wafer into water, and the 2D material will delaminate with the substrate, so they will float on water automatically. This is actually the way how we transfer 2D material, the TMD material, to be a freestanding material, is just to delaminate the water and then just scoop them using a TM grid, which actually avoid a lot of contamination using polymer. So it's a very good way, a clean transfer method.
Okay, I think we've reached the top of the hour. If there's more questions, please come see Cong up here. Else, thank you all for coming.
Yeah. Thank you so much.
What other time?
No, you're AF. Yeah.
Excellent.
Oh,
Nice
thank
talk.
you.
Yeah, great.
Well, I apologize for that coughing.
No, that's yeah.
When I speak sometimes I feel like too dry in my throat, and it just happens.
Yeah, no, I think it happens to me also here. Like when the air is very dry, and then like, at some point it's just like it's fine, no worries.
Talk too much today, so. But yeah.
Well, that was great. Perfect. Excellent. So yeah, we did some HBN work, also on emitters, but not for EV with microscope. And then there was this an effort to try co-local, but like sort of ex situ optics, in situ T. I mean,
You guys
then
are
put
trying
it
to
in
I
TM.
bring you down.
It's very hard. So
Just look at the
well, I think
experiment.
they
I'm not
collaborate
really
with
involved
the
UT
UT Austin.
Austin,
Yeah. Jamie Warner.
Jamie Warner,
Yeah.
exactly. Yeah.
I know that.